Hello everyone, and a warm welcome to the UCL Queen Square Institute of Neurology. My name is Max.
And I'm Isabel, and we're hoping to teach you a bit about MRI scanners today. We're going to start you off talking about the different components in the scanner, if you would like to follow us through. We're now in the MRI control room. As you can see behind us, behind this screen, we have a large tube in which we have a large magnet. The table is where the patient lies and is brought to the centre of the magnet. The scanner uses magnetic fields to produce detailed images of components inside the body without the use of harmful radiation. The scan time depends on the area being examined, but it can take up to 90 minutes. A radiographer controls the scan from a separate room using a computer system. And as you can see, it projects thin slices of the body. We're now going to talk you through the important components of the scanner.
There are three main components required for the MRI to work. First, the main magnet, second, the RF coils, and third, the gradient coils. The main magnet is used to create the static magnetic field. Most MRI magnets use a magnetic field of 3 Tesla. The Earth's magnet is only 0.00005 Tesla. There are different types of magnets. Superconducting electromagnets are most frequently used. Radio frequency coils are used so we can see the MR signal. They may be considered as the antennas of the MRI system. The radio frequency coils have 2 functions, transmit and receive. The RF coil transmits the excitation pulse, which rotates the net magnetization away from the main magnetic field in the Z plane to the transverse XY plane.
I'm now going to tell you about the benefits and the disadvantages of MRI scanners. We've already told you a bit about the benefits, but these include that it's non-invasive and that it's non-ionizing, so it's not harmful for the body as opposed to CT. It also gives you very good soft tissue contrast, also as opposed to CT, and it can give you good 3D images. I'm now going to tell you about the disadvantages of the MRI scanner, and that is why there's always sort of safety signs outside every scanner room. I don't know if you can hear it, but the scanner makes very loud noises, and also if you looked at the tube earlier, it can be very claustrophobic. It also cannot have, because it's a big magnet, you cannot bring in metal objects into the scanner room, so often patients with pacemakers, for example, are advised not to have a scan done. It is also worth knowing that MRI scanners, the machines, are very expensive.
And now we will take you through the basic physics of MRI.
The human body has millions of hydrogen protons moving around randomly. They are said to each possess a magnetic moment. When the body is placed within the main magnetic field, the protons align themselves in the direction of the magnetic field. Now the protons spin around the axis of the magnetic field. This spinning motion is called precession. It occurs at a specific frequency, described by omega, which is proportional to the strength of the magnetic field, also called BO, by the gyromagnetic ratio, a constant specific to the type of tissue being imaged. This frequency is known as the Larmor frequency, and hence the equation is called the Larmor equation. These protons sum up their magnetic moments in the axis longitudinal to the magnetic field. This sum is called longitudinal magnetization. However, it cannot be measured in this plane. To measure it, we need to move away from the magnetic field direction. We do this using a radio frequency pulse, which is produced by the RF coils. When the RF pulse is turned on, it flips the longitudinal magnetization to the transverse plane, creating transverse magnetization. When the RF pulse is turned off, 2 things happen. First, the transverse magnetization begins to decay. The time it takes to do this is called the T2 relaxation time. Second, the longitudinal magnetization grows back to equilibrium. The time it takes to do this is the T1 relaxation time. Different tissues in the body have different T1 and T2 relaxation times. This allows us to distinguish them on MR images. This is called tissue contrast. During the T2 decay, the transverse magnetization releases its energy. This energy is emitted as an MRI signal. It is detected by the radio frequency coil and used by a computer to create an MRI image. 3 different gradient coils can be applied to vary the magnetization in space, in the X, the Y, and Z directions. This helps us to determine the location of the signal within the body.
Terranova MRI is a dummy MRI used for learning and research purposes. It uses 2D and 3D magnetic resonance imaging. We can use experiments to enable us to explore more complex ideas with a hands-on approach. Terranova uses the Earth's magnetic field as the B0 and uses the same components with a lower magnetization. Instead of using participants, we can do MRI on objects such as a water bottle or an orange. Here is an image to show the Terranova components. The software has tools to reconstruct and better visualize the data. This is an example of imaging an orange using the Terranova MRI. And now a little quiz to refresh our memories. These questions are based on previous A-level exam questions. Question number 1. Outline the basic principles of a magnetic resonance scanner used to scan a patient's brain. Any of the following answers would give you a mark. The head is placed in a superconducting magnetic field. A radio pulse excites hydrogen nuclei. When hydrogen nuclei change alignment, they emit a radio signal. These signals are detected and passed to a computer. Gradients in a static field allow location to be determined. Question number 2. State and explain 2 advantages and 2 disadvantages of using an MR scanner to scan a patient's brain compared with a CT scanner. For advantages, any of the following answers would be correct. MRI does not involve ionizing radiation and has no harmful effects. It is better at distinguishing soft tissue than CT. And it can show 3D and cross-sectional images. Any of the following disadvantages would also give you a mark. MRI cannot be used if the patient has a metal implant, for example a pacemaker. The patient might have to lie still for up to an hour, and it is also very expensive.